In this lesson, we will explore how to read and compare sinusoidal graphs by identifying and describing key features. So interpreting sinusoidal functions. So we want to take the key features that we've already learned and observe them on these different sinusoidal functions and then compare them. So two students are riding their bikes. A pebble is stuck in the tire of each bike. The graph below shows the heights of the pebbles above the ground in terms of time. So if you can tell here, we have height in centimeters, which is represented by the variable h, and then time in seconds, represented by t. We have two bikes. We have bike A and bike B. Bike A is in black and bike B is in pink. So both are definitely sinusoidal functions. They look to keep repeating. So many cycles are shown on the graph. Now looking at the scales, our height goes up by 10, our time goes up by 0.2 seconds. So keep that in mind because that we have to interpret it and we're gathering information from the graphs. So what information can you gather from the graphs of the two functions? So looking at bike A, we're going to compare peaks and then bike B. So bike A in black, we can tell that the highest point is 60 centimeters. We're going to say 60 centimeters. Looking at bike B in pink, the highest point would be 50 centimeters. Troughs, let's compare our minimums. So when we're comparing our minimums, our lowest point, both are, should put that back out there, 0 centimeters. 0 centimeters. The periods, when does one full cycle occur? So keeping in mind, we said the scale is 0.2, 0.4, 0.6, 0.8, and then 1. Okay, so when we're looking at bike A, it does start at the max there. So from here to here, that would be 1 period. So that's our cycle. That means one full cycle occurs between 0 and 0.6. So this is bike A. So because it's 0.6 minus 0, we know that 1 cycle occurs in 0.6 seconds. We're going to do the exact same thing looking at bike B. It's a different color. Let's see, is blue. At this time, we're not going to start max to max. We're going to start min to min. So there's the min to min. So that looks like to 0.0.5. Okay, so that's when one full cycle occurs. From here to here. That's one cycle. Okay, so in this case, it would be 0.5 seconds. Okay, so we're going to compare the equation of axes. Again, we know that we can take the max plus the min divided by 2. We can interpret it on the graph as well, the halfway mark. So from 0 to 60, we know that halfway between should be 30. So let's just calculate that. Because it's y equals, we're going to say h equals max, which is 60 plus my min, divide that by 2, h is equal to 30. Likewise, h is going to equal to 50 plus 0, divide that by 2, h is equal to 25. Now let's see if that is the case when we look at our graphs. We're going to do, because it's black, let's say halfway mark. Does that look like at 30 for the black graph? Absolutely. So this is h is equal to 30. And let's put that in pink if we can. 25, absolutely. It looks like it's that halfway mark for sure. So h is equal to 25. Okay, so next we want to compare the amplitude. So when we can read that right off our graphs, because then we have the equation of axis and the amplitude is that distance from the equation of x to the max or to the min. But let's use our equation to calculate that. So we have max minus our min, so 60 minus 0, divide that by 2. The absolute value of A is equal to 30. Likewise, max minus our min, divide that by 2. Amplitude is equal to 25. And again, if we put units, that would be centimeters. Okay. Okay, that just goes to show, if you remember, from the center to it, that would be the radius of our wheel. Okay, and that's what the amplitude would represent. Now, looking at our graphs, definitely, if you look at the equation of axes, 30 to 60, that would be 30 for sure. And then 25 to the peak 50 would be 25. Okay, now let's compare speeds. So when we're looking at the distance, we need to know that circumference, what it covers in one cycle, right? So if that is the case, that circumference of a circle would be that circumference equals 2 pi r. So let's figure that out first. So what is that distance? Because remember, for any kind of speed, speed is always the distance over time. So velocity is always speed or velocity is always distance over time. Not sure if you remember this triangle that you used. Velocity is distance over time to help remember the different properties of speed. Okay, so to figure out the distance, what the pebble covered, right, is going around that circle would be distance, we're going to say, is that circumference of the wheel, which is 2 pi r. Now the radius is that amplitude. So we're going to say times 30, which is 60 pi centimeters. Okay, that pebble, when it goes around that tire, every time it's covered 60 pi centimeters. So the speed, which we said was distance over time, we know the distance, which was 60 pi centimeters, the time, which we know it took one full cycle to occur. It took 0.6 seconds. Distance over time. Simplifying that would be 100 pi centimeters per second. Or if we put that into decimal, about 314.16 centimeters each second. Now, looking at the smaller bike, which had a smaller radius, the distance that pebble covered would be 2 pi r. 2 pi, the radius was 25, so it would be 50 pi centimeters. Speed is always distance over time, which is equal to 50 pi over, it took 0.5 seconds, which is 100 pi centimeters squared, which is about 314.16 centimeters per second. Okay, so traveling at the same speed, however, the radius of the tires are smaller. So, okay, moving on to example number 2. We have Olivia was singing back and forth in front of a motion detector when the detector was activated. Her distance from the detector in terms of time can be modeled by the following graph shown. So distance is in meters and time is in seconds. What is the equation of the axis and what does it represent in this situation? Again, we're given a graph. In order to calculate the equation of axis, we do need the maximum and we need the minimum. So remember, max plus min divided by 2 is the equation used to calculate the equation of the axes. So let's do that. So we know the max is equal to 14 and the min is equal to 2. So what is the equation of axes? We're going to say dt is equal to 14 plus 12, divide that by 2. 14 plus 12, which is 16 divided by 2, which is 8. Let's see, does that look like it? Sure does. Okay, so what does that mean? The equation of axes. So the equation of axes is d at t is equal to 8, and it represents the resting position of the swing. Okay, what would be the amplitude of this function? Well, we know amplitude is always max minus or min, so 14 minus 2, all divided by 2, which is equal to 6. So what is the amplitude? Therefore, the amplitude of this function is 6 meters. What's that? What is the period of the function, and what does it represent in this situation? So the period, again, we know is when one full cycle occurs. So looking at that, if you scroll up here, in this case, because we have a minimum to the minimum, so that would be 1, 5. Okay, so we can say period is equal to 5 minus 1, which is 4 seconds. So that means one full cycle occurs 4 seconds. So that means in this case, because is the action of the swing, that means this is when one full complete swing occurs. So we can say, in this case, what is the period of the function of the function is 4 seconds, and it represents the time it takes for Olivia to complete one full swing. Okay, how close did Olivia get to the motion detector? Okay, so we have to interpret that from the graph. So when looking here, oh boy, the minimum. And if you look on the graph, the closest she got was 2 meters. Okay, so never 0 would be where the motion detector was. Her minimum is 2. So we can say from the graph, the minimum distance between Olivia and the motion detector is 2 meters. So the closest Olivia got to the motion detector was 2 meters. Okay, if a motion detector was activated as soon as Olivia started to swing from rest, how would the graph change? Would the resulting graph be sinusoidal? Okay, so I think that because she wasn't at a continuous swing, the graph would not show the same repetitive graph. Okay, so the cycles would be different. Okay, from rest, because think about when you're on the swing, you have to like slowly build up momentum. So there wouldn't be a repetitive pattern. The Y values wouldn't stay the same. It's like sure, and it would just not be a sinusoidal periodic function. So if the motion detector was activated as soon as Olivia started to swing from at rest, the amplitude of each cycle of the graph would increase up until the amplitude, so there'd be varying amplitudes, became 6 meters. Therefore, the graph would not be sinusoidal because the amplitude would be changing. And the varying amplitude doesn't stay the same, so therefore it's not a sinusoidal function.